Hey Math113, welcome back to part 2 of our discussion about complex numbers and I like to say DeMoivre's theorem, but really it's DeMoivre's theorem. And I am not French and I don't even come close to that. But anyway, so in the part 1 of the video, we talked about a few things. First of all, we reminded ourselves of what complex numbers actually are. Okay, we plotted complex numbers in the complex plane. And then the last thing we did is change a complex number from rectangular form, which is just that regular old a plus bi form, to polar form. And just to make sure you feel comfortable with that operation, because you have to do this a lot, I want to do another problem where we're given a z value, which is just a complex number, 2 minus 2i. We're supposed to plot that in the complex plane and then write z, which right now is in rectangular form of 2 minus 2i. We're supposed to write it in polar form. Now, when you write a complex number in polar form, you need to be told whether this should be in degrees or in radians. And when you work on the homework or the test, that's going to be clear. I did not specify in these problems whether it needs to be in degrees or radians, so really both would be correct. I'm going to do both, or either one would be correct. I'm going to do both so you see it happen. Okay? Now first let's plot it. 2 minus 2i. Remember, this is the real part, and I want to plot 2, this first 2 here, along 2, but you can't plot it yet because you have to do the minus 2i as well. So this point here, the pen is not working. Hold on. So 2 minus 2i, there we go. There is that in rectangular form plotted in the complex plane. Now to change this to polar form, you have to first find the modulus and the argument, and then you can write it in this form that I'm circling in the definition after you find the modulus, which is r, and the argument, which is theta. So the modulus formula is right here. That's also called the absolute value of the complex number. So if you find r, again, that's called the modulus. You're finding the square root of a squared plus b squared. A is 2, so don't forget to square it. B is negative 2. You do not include the imaginary, the I value, in your modulus formula, or if you're finding the absolute value, which is a number's distance from 0. So 2 squared is 4, plus 2 squared again is 4. That gives me the square root of 8, which needs to be simplified as 2 square root of 2. Okay, and I know you don't need me as a trig student to explain where that came from. You rewrite 8 as 4 times 2, the square root of 4 is 2, and the other 2 stays underneath. Now let's find the argument, which that is tangent of theta is equal to, I always think of y over x, but in our problem that's b over a. So my b value is negative 2, that goes in the numerator. My a value is positive 2, that goes in the denominator. So we need to know at what angle is tangent of theta equal to negative 1. Okay? Now let's think about that. Tangent is negative in 2 quadrants. It's negative in quadrant 2 over here. So remember, this is quadrant 2. And it's also negative in quadrant 4. Now my answer must be in quadrant 4 because when I plot my complex number, that's in quadrant 4. So where is tangent of theta equal to negative 1 in quadrant 4? That's at 7 pi over 4. Okay, so this angle is 7 pi over 4. If you were to write that in degrees instead, now me, I think in terms of radians, because really radians are real numbers, degrees are not. So I multiply, if I want to change it, 7 times 180 divided by 4 gives me 315 degrees. Now some of you are used to thinking in degrees, but I've even let that go out of my brain. I'd rather just do the conversion, okay? So either one of these will work depending on the way the question asks the problem. Now, they're not asking you what is the modulus, what is the argument. They're asking you to write this in polar form. So the answer to this in polar form, the number 2 minus 2i is, my r is, where'd you go, 2 square root of 2, and then parentheses, and you have cosine of 7 pi over 4 plus I sine of 7 pi over 4. If the problem asks you to write your polar form in radians, that would be what you did. If it asked for degrees, you would write 2 square root of 2 cosine of 315 degrees plus I sine of 315 degrees. Okay, so the hard part is not whether it's in degrees and radians. You can figure either one of those out. I have found in the homework that they tend more towards degree form than radian form, but you need to be able to do both. Now, what if we're asked the opposite? We're supposed to write z equals 4 times the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6 in rectangular form. So I know you can tell this is polar form. How do you know? Well, it's got the I in it, so you know it's a complex number, and it's got the trigonometric functions in it. So that is definitely polar form. Happens to be in radians, but remember this could be radians or degrees. This one's easy. You just have to evaluate it. Now, sometimes you will get decimals as answers. Sometimes it wants exact values. So let's just figure out what the answer to this is. Feel free to use your calculator. Now, be careful. If you're using your calculator, it needs to be in radian mode, right? And if you have to have exact answers, your calculator may do trig functions and give you decimal answers. So just be very careful about how homework or tests want your final answer. Now, I'm just going to do this work in my head and not touch my calculator unless I have to. Let's just see how it goes. So again, I've got z equals, remember we call complex numbers, we usually use the letter z, 4, and I'm going to go ahead and evaluate the cosine of 5 pi over 6. Now, for me to do this, this is just my brain, my math brain, I have to have a unit circle visualized in my head. 5 pi over 6 lives right down here, almost at pi. Cosine is the x value there, which is negative. That is negative square root of 3 over 2, right? Plus I, and that sine of 5 pi over 6. Now the sine right there is the y value right there. That's the short one, 1/2. Now I wrote I first, then 1/2. Really the better way to write that is 1/2 I, but I'm still not finished because I have to distribute the 4. So z is equal to, now, excuse me, if I multiply 4 times negative square root of 3 over 2, the 2 and the 4 are going to cancel, and that's going to give me negative 2 square root of 3. And then 4 times 1/2 gives me plus 2i. Now this is exact values, and sometimes you're asked to find exact, sometimes you're asked to find your answer rounded. Let's do 1 decimal place. Just be really careful when you read directions. I did not specify either way, so I'm doing it both ways. So I'm just going to type in, and again, when you do it in decimal form, there's absolutely nothing wrong with using your calculator to evaluate every bit of this, but you must be in radian mode. If you're not going to get the right answer when you evaluate cosine of 5 pi over 6. So if I just type in 4 times the cosine of 5 pi over 6, that's going to give me right off the bat negative 3.4, or negative 3.5. Remember, I'm rounding 1 decimal place. And then I'm going to type in 4 times sine of 5 pi over 6. 5 pi over 6. I'm actually typing it in, and that gives me 2. Now, that's not a surprise. I'd already gotten 2. Don't forget your I. But I wanted you to see it done that way as well. Okay? So, changing rectangular form of a complex number to polar form of a complex number, you have to find the modulus, which is really the absolute value of the complex number, and your argument, which is the theta. You just tangent of theta equals b over a. And then to go the other way, you just evaluate it. What do we have now? Okay. What if we need to multiply complex numbers together? This is the product of 2 complex numbers in polar form. So we're going to let z1 equal r1 cosine of theta 1 plus I sine of theta 1. So notice that is just a complex number in polar form. Okay, Z2 is going to be R2 cosine of theta 2 plus I sine of theta 2. And again, that is just a complex number in polar form. Check out the result. If you want to multiply Z1 times Z2, this is pretty neat, then you would multiply R1 times R2. So you multiply the modulus of the first one times the modulus of the second one, or the moduli together. Okay, R1 times R2. And then check this out. Have cosine of theta 1 plus theta 2. Okay, remember the theta is the same for the real part and the imaginary part. So you just add the theta from the first number to the theta from the second number, and then plus I sine of the same thing. Theta from the first number plus theta 2, or theta of the second number. Now, how might this formula be developed? Where in the world could this formula have come from? Well, let's talk about it, okay? So let's just multiply two general complex numbers together, just like the form we have above, okay? So Z1 times Z2 is R1 cosine of theta 1 plus I sine of theta 1 times R2 cosine of theta 2 plus I sine of theta 2. We're multiplying, right? Now this R1 right here and this R2 right here, can't I go ahead and just multiply those together and say that's R1 times R2? Because this is just multiplication, all right? And that's what I did in this step. So I put R1 times R2 together, and then my parentheses, cosine of theta 1 plus I sine of theta 1, and cosine of theta 2 plus I sine of theta 2 together. Now my next question for you is, how are we going to multiply this complex part times this complex part? How would we do that? Well, FOIL. Don't you think? I mean, I'd have to multiply this times this, this times this, this times this, this times this. That's my next line. Okay, see if it looks right to you. So cosine of theta 1 times cosine of theta 2. That's what I have here. Okay, and then that's first outer cosine of theta 1 times I sine of theta 2. That's right here. I put the I in the front so I don't get lost with it. Cosine of theta 1, sine of theta 2. And then I multiply the insides together. So I sine of theta 1, cosine of theta 2, that's here. And then finally the outsides. Now be careful here, because that's an I times another I. That gives me I squared. And sine of theta 1 times sine of theta 2 gives me sine of theta 1 times sine of theta 2. Okay? Now, next, what could we do? Well, one thing that I noticed is I got an I squared right here. Remember what I squared is equal to? Yes, -1. I know you all said it in unison together. Yay! I squared is equal to -1. So I'm going to replace this I squared right here with -1. Now, that leaves me with this guy and this guy. They both still have I values. Those terms do. But this one, I'm going to underline this one in green, and this one do not any longer have I values, because this I squared is -1. So what I'm going to do is I'm going to group these two together. So cosine of theta 1, cosine of theta 2 minus sine of theta 1, sine of theta 2. And then I'm going to factor out this I right here, cosine of theta 1, sine of theta 2, plus cosine of theta 2, sine of theta 1, or you could rewrite this as sine of theta 1, cosine of theta 2. If you put your sines first, then your cosines. Is any of this looking kind of familiar? Like, if I write the green ones together, that's cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. Does that look familiar? Need me to help you out a little bit? How about these guys? Sum and difference formulas. Remember those guys right there? So cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta... Look, that's that. So instead of writing this, which is what we had after we changed I squared to -1, I'm going to write this instead. Now, we don't have alpha and beta. We have theta 1 and theta 2. And look, there's that part right there in the formula. Okay, now I'm going to flip screens on you again. If I go back to the red part, okay, I factor out my I. So that's going to be I comes out, and that is cosine of theta 1 sine of theta 2 plus sine of theta 1. I'm rearranging this order, cosine of theta 2. Why? Because our formulas are usually written like that. Okay? Now, let's see what formula that is by clicking back over. So it's cosine sine plus sine cosine. You see that? Cosine sine plus sine cosine? Sort of. Right here. This is sine cosine plus cosine sine. Oh, yeah. So this one's first, cosine sine plus sine cosine. That is sine of alpha plus beta. That's this guy right here times I, and look, there it is right there, okay, where we have theta 1 plus theta 2. So instead of rewriting every single line, that's pretty much the proof for it. You just multiply all that out by hand, use some difference formulas, and there's your formula. Now, I'm not going to ask you to memorize the proof of that, but I do need you to know this formula. And if you do your homework, you're going to know it. Okay, so you multiply your two moduli together, then you add your two angles inside cosine, and don't forget to write your I, and then add your angles inside sine. So let's actually do a problem like that, and you're going to realize it's pretty easy, just a little bit of calculation to do, okay? All right, so Z1 is 4 cosine of 15 degrees plus I sine of 15 degrees, and Z2, 7 cosine of 25 degrees plus I sine of 25 degrees. So if we find Z1 times Z2, remember the first thing you're supposed to do right here is multiply your moduli together. So that's going to be 4 times 7. I'll multiply it in a minute. And then that's going to be cosine of theta 1 plus theta 2. So my theta 1 is 15 degrees. Plus theta 2 is 25 degrees, okay? Plus, don't forget your I, sine of theta 1 plus theta 2. So that's going to be 15 degrees plus 25 degrees, okay? Now to leave it like that, simplify. 4 times 7 is 28. That can stay out front, okay? Times the cosine, 15 plus 25 is 40 degrees, plus I times the sine of 40 degrees. Now here's one drawback of your homework. Instead of asking that you type this entire answer in, they're going to put a block right here, a block right here, and a block right here. Which means that you don't get the luxury of typing that in every time and truly memorizing the formula. So promise me when you do your homework, you will do it all the way out. You won't quit halfway in the middle of a problem because you know what those blanks are. Matter of fact, you could just look at this problem and go, oh, 15 plus 25, that's 40. Ooh, 4 times 7, that's 28. And just type all that in as fast as possible. You could be done just like that. But please write it down. The only way you truly understand what the answer is by writing it down. It's not just 28, 40, and 40. The true answer is 28 times the cosine of 40 plus I times the sine of 40. You know, I'm being a picky math teacher, but that's the truth. You really need to write this down. I also want to point out that sometimes they ask you to leave this in polar form, just like I did here. And sometimes you're asked to put it in rectangular form. And if that's the case, I would type this in my calculator. I would do 28 times the cosine of 40, and write that down, and then do 28 times the sine of 40, and then write I times that answer down, okay? Now, what about division? What if we want to divide two complex numbers? Let's look at this formula, okay? So Z1 over Z2, notice it's written in fraction form. You first do R1 divided by R2, and check out this fun. You do cosine of theta 1 minus theta 2, and I sine of theta 1 minus theta 2. Now, I don't prove this one like I proved the last one, but essentially the idea is the same. You divide the moduli, and then you FOIL, well, you're doing division, okay? And you work through that division, use sum and difference formulas, and then there's your proof. But I'm not going to go into that one. I just wanted you to see the other one, but I do want you to be able to use it. So why don't you pause the video, do this problem on your own real quick, see how it goes, okay? All right, how did it go? Seemed pretty good? Let's do it together. So I'm supposed to find Z1 divided by Z2, which would be different than Z2 divided by Z1, so be careful about that. Now, our moduli are 3 and 10, so it's going to be 3 over 10, and then parentheses. Remember the formula, or you can look at it right here. Cosine of theta 1 minus theta 2. That's going to be the cosine of 5 pi over 18 minus pi over 16. Remember, your theta 1 is in the first polar form complex number. Your theta 2 is in the second polar form complex number. Plus I sine of 5 pi over 18 minus pi over 16. Okay, 3/10 is simplified. I guess if you had to, you could change that to 0.3. But if you need exact values, well, I don't know, just read your directions, okay? Now, 5 pi over 18 minus pi over 16. If you want to cheat your way through that, I would just type 5/18 minus 1/16 in my calculator, leave the pi out of it in fraction form. So 5/18 minus 1/16 gives me 31 over 144. So this is going to be the cosine of 31 over 144 pi. It's not nice. We could have done that one by hand, but who wants to do that? Finding a common denominator business for this one. So again, 5 pi over 18 minus pi over 16. I typed in 5 over 18 in my calculator using the fraction button minus 1 over 16 and just put the pi with it. And again, that gives me 31 over 144 pi. And if it asks for it in rectangular form, I need to evaluate this. If it wants it in polar form, I am good to go just like that. Okay, now let's sum up what we've done so far. Again, we started with complex numbers, remember, and those basically came from solving quadratic equations when you had negatives under square root, right? We talked about graphing them in the complex plane. Then we found the absolute value of them, which is the number's distance from 0. And then we decided to write them in polar form, and all of a sudden trigonometry was involved. Next, we multiplied two complex numbers together, and then we divided complex numbers. Now let's talk about raising a complex number to a power, say raising a complex number to the second, third, fourth, fifth power. How could we do that? So let's walk ourselves through this idea. Okay, we can use a formula to find powers of complex numbers if the complex numbers are expressed in polar form. Why would this work? Now, what if we weren't doing this in polar form? Let's think about what we would have to do here. So let's just say I gave you the complex number 1 minus 3i, and I wanted to raise it to the fifth power. What would we do? Well, what does that really mean? Well, that's 1 minus 3i times 1 minus 3i times 1 minus 3i. Maybe she shouldn't have made it to the fifth power. I know what you're thinking. 1 minus 3i, right? 1, 2, 3, 4, 5 of them. Now, how do we multiply those together? Well, we did one. Remember, at the beginning of part 1, we multiplied, let's just say, these two together. And you'd have to FOIL it, right? 1 times 1 minus 3i minus 3i plus 9i squared would be 1 minus 6i minus 9, because remember, I squared is negative 1, which will give you negative 8 minus 6i. That's just for the first two. Then I'm going to have to take that and multiply it times this next 1 minus 3i. How am I going to do that? I'm going to FOIL it, and I'm going to do all the same steps I just did, right? How long is this going to take? Longer than I want. Way longer than I want. Now, there are methods to do this a little bit faster than just multiplying them two at a time together, but it's still a lot of work. Trust me, it's a lot of work. I know you already see what's going into this. So if there could just possibly be an easier way to raise a complex number to a power, then that would be way better, right? If you might not even be thinking about why you might need to raise a complex number to a power. Don't worry about that just yet. I've got a good answer for that in a minute. But how would we do it? How could we make it a lot easier than all of that I didn't even finish just a minute ago? Well, we can do this in polar form instead of rectangular form of a complex number. It said this formula can be illustrated by repeatedly multiplying r times cosine of theta plus I sine of theta. So let's do that just for a little bit, okay? So there is my first number. Remember, we call complex numbers z. And I've got r cosine of theta plus I sine of theta. Now let's find z squared, right? Which would be z times z. So I'm going to multiply z times another one. So I've got in black my original z, and then in pink over here my new z. Now how do we multiply those together? Well, you just learned how to do it, right? So r times r, remember, is r squared. You multiply the moduli together. Then you do cosine of the first theta plus the second theta. Okay, well, theta plus theta, 2 theta, right? So this is going to be r squared up front, cosine of, I add those thetas together to get 2 theta, and I do the same thing for sine, okay, using the formula for product. And you'll see the results right here. This is what I just mentioned, and it comes from what I highlighted for you over here in yellow. That's our formula for multiplying 2 z values, or complex numbers that are in polar form together. You can only do this when they're in polar form, okay? Well, let's do z to the third. You want to? Well, let's do it anyway. Okay, so z to the third is going to be z squared times z. So here's my z squared, which is r squared cosine of 2 theta plus I sine of 2 theta, times my new one, my pink one over here, which is going to make that z to the third. Now, again, how do you multiply complex numbers together in polar form? Well, you multiply your moduli. R squared times r is r to the third. And then what do you do with the angles? You add them. So this is going to be cosine of 2 theta plus theta. That's going to be the cosine of 3 theta. And I sine of 3 theta. So that's the next line I have that popped up for you. There you go. So r to the third, cosine of 3 theta plus I sine of 3 theta. Now you're looking for pattern. You notice the pattern? If you're raising it to the third power, then your r is to the third power. Your angle shows up 3 times, so it's 3 theta in both of them. So I bet you could guess what z to the fourth would be, right? And you probably shouldn't guess in math. You should probably do the work. So z to the third times z would be z to the fourth. Then remember, the rule is you multiply the moduli together. So r to the third times r is r to the fourth. Then what do you do with the angles? When you multiply, you add them. So inside cosine, I'm going to have 3 theta plus theta is 4 theta. And then the side sine, I'm going to have 3 theta plus theta, which is 4 theta. So check it out. Z to the fourth would be r to the fourth, cosine of 4 theta plus I sine of 4 theta. Now, if you just keep following this recursive pattern, you're going to get a formula, which is right here. So if you want to raise z to the n power, then you do the modulus to the n power, so that's going to be r to the n, and you do your angle times n. So it goes here and here. Okay? And this is called DeMoivre's theorem. Now, again, I just want to say DeMoivre because that's just so much easier for me, and I've heard that for so many years. But DeMoivre's theorem is named in honor of the French mathematician Abraham DeMoivre, and he lived from 1667 to 1754. You notice how we're moving up in the mathematics years? That's kind of cool, okay? So we're supposed to use this theorem to find the power, write the answer in rectangular form. So be really careful again with your homework and in what form your final answer is supposed to be. So we're supposed to find z to the fifth. Notice it's already raised to the fifth out here. Remember, the first thing you're supposed to do is raise your modulus to the fifth power. So this is going to be 1/2 to the fifth power. And it's going to be times the cosine of, because we're raising it to the fifth, I have to do 5 times pi over 10 plus I times sine of, once again, 5 times pi. Doesn't look anything like pi. Let me try that again. 5 times pi over 10. DeMoivre's theorem is pretty easy when you start working with it. So 1/2 to the fifth. Remember, when you take a fraction and you raise it to an exponent, it's 1 to the fifth. You do the numerator to that power, and you also do the denominator to that power. So 2 to the fifth, we know is 32. And that's going to be cosine 5 pi over 10. I cancel my 5 and 10 to get pi over 2. Plus I times the sine That should also be pi over 2, but it's worth checking it again just to be certain. Okay, now this is in polar form. Now notice the directions didn't ask for it in polar form, but there it is just in case. Now what do you do to change polar form to rectangular form? You evaluate it, okay? So you've got 1 over 32, the cosine of pi over 2. Y'all picture that unit circle in your head, right? Pi over 2 is at the top of the unit circle, straight up or at 90 degrees. What's the cosine at 90 degrees? That's the x value at 0, okay? Plus I times the sine of pi over 2. Again, pi over 2, top of your unit circle. Sine is the y value there. The y value at pi over 2 is 1. Okay, so I distribute 1 over 32 inside. Well, 1 over 32 times 0 is just 0. So really, this is just going to be 1 over 32i. That is in rectangular form. I've reached 30 minutes, so I want to come back for part 3. Yes, I have more to cover, and we will practice this a little bit more, and then we'll talk about finding roots. Instead of raising complex numbers to a power, we're going to find roots. I hope this is all going okay. You have a wonderful day.